In this video, I'll cover the basics of how to balance a redox reaction. Again, redox reactions are reduction reactions that are coupled together for electrons to be transferred from one species to another. In balancing redox reaction, there are a series of steps that you must follow in order for you to be able to successfully balance a redox reaction. I'm going to go through each of these steps with an example. For a redox reaction, you might get a question like balance in acid the following equation. We've got nitrate, NO3 with a -1 charge, plus chloride, Cl -1, yields nitrogen, N2, plus chlorine, Cl2. For each of these, we should start with step 1, which tells us that we should identify the oxidation number for each element in our reaction. So we'll look at our reaction here, and we'll identify oxidation numbers. Some of them are pretty easy. So for example, N2, each of them has an oxidation number of 0, and Cl2, each chlorine has an oxidation number of 0 also. On the other hand, when we look at our species on the reactant side, we see Cl- is pretty straightforward, where each chloride has a charge of -1. For the nitrate, we know that unless an oxygen is just as oxygen gas, or if it's in a peroxide, each oxygen atom will have a charge of -2. What I like to do is I like to put the charge for individual elements above the element, and then the total charge associated with that element below. So if we have 3 oxygen atoms, that's a total charge of -6. Because we have the negative charge on the nitrate, what we're going to do is we're going to set that whole thing equal to -1. That means in this case, nitrogen is going to have a charge of +5 to balance out the -6 to give a total charge on nitrate of -1. So we've successfully accomplished our first step. Our second step tells us to balance any elements besides hydrogen and oxygen. So we can look at the reaction we have, and we can see that for the nitrogen, we only have 1 nitrogen as a reactant, but we have 2 nitrogens as a product. So we're simply going to write a 2 in front of the nitrate. The same is true for chloride. We have 1 in the reactant and 2 for the products. So we're going to put a 2 in front of the chloride. We'll worry about balancing any oxygen or hydrogen later on, so we've accomplished step 2. Our third step is to determine which elements are being oxidized and which ones are being reduced, so that we can then split into half reactions. So for one of our reactions, we'll notice the chloride is going from a -1 to a 0. So each chlorine is losing 1 electron, and what that tells us is that if we're losing electrons, this is oxidation. On the other hand, we can see that our nitrogen, each one is going from a +5 to a 0, so that's a gain of 5 electrons per nitrogen. So we're going to refer to this as reduction. Forgive me as I'm running out of space here. So that accomplishes step 3. The next step tells us that we need to split our oxidation and reduction reactions into half reactions. So what we're going to do is we're going to take one of our reactions, which is the chloride reaction, where we've got 2 Cl- going to Cl2, and our other half reaction is going to be 2 nitrates reacting to form N2. So we've accomplished step 4, splitting into 2 half reactions. The next one says balance oxygen by adding water to either side. So in our first reaction, there's no water. We don't need to add anything there because we don't need to balance any oxygens. On the other hand, our second reaction, we have 2 nitrates, and each nitrate contains 3 oxygens for a total of 6 oxygens that need to be balanced. So we will add 6 water molecules to our product side to balance the oxygen. So we've successfully accomplished our next step of balancing the oxygen. Now we're going to balance hydrogen by adding H+ to either side. What you'll see here is that in our first reaction there's no hydrogen to balance, but in the second reaction we have a total of 12 hydrogen atoms that need to be balanced. So we'll add 12 H+ to our reactant side. That accomplishes step 6, and we can move on to step 7 to add electrons to balance the charge. So you'll notice in our first reaction, the total charge on the reactant side is a -2 because each chloride has a -1 charge, whereas the chlorine does not have a charge. So we can balance that total charge by adding 2 electrons to the product side for this half reaction. Now for our second half reaction, you'll notice that we have 2 negative charges from the nitrate plus 12 positive charges from the hydrogen. So we can simply write for ourselves -2 plus 12 gives a total charge of +10. And on the other side of the reaction, we don't have a charge at all. So to make those equal, what we'll end up doing is we'll simply put 10 electrons on the reactant side. So that takes care of step 7, but you'll notice I added a second part of step 7 which says double check that the electrons match the electron transfer in the original reaction. So if we look back at our assignment, we'll notice that for the chloride to chlorine reaction, we have a loss of 1 electron per chlorine atom. That would give us a total of 2 electrons because we have 2 chlorine atoms. And we'll notice that that is replicated in our half reaction above. Similarly, we can look at the nitrate to nitrogen reaction, and in that case we had 5 electrons per nitrogen. There are 2 nitrogens, so we can say that should be a total of 10 electrons. And we can confirm our balancing of our half reaction because we can see we added 10 electrons to the reactant side of that half reaction. So we're done with step 7. We can move on to step 8. Step 8 tells us that we need to multiply the half reactions to have equal number of electrons on both sides. So we'll look at our reaction and see that we have 2 electrons for the chloride half reaction and 10 electrons for the nitrate half reaction. So for us to have a common denominator between the two, we're going to need to multiply our top reaction by 5. So let's mark that multiplication. So then we should end up having 10 chloride ions, 5 chlorine molecules, and 10 electrons. So we've taken care of step 8, and now we just need to add the 2 half reactions together. I'm going to erase the bottom of the board so I have plenty of room to write that out. So in step 9, we're simply going to add together the 2 reactions. You'll notice these are the 2 reactions that we're focusing on, our 10 chlorides and our 10 electrons associated with that half reaction, and then we've got 10 for the other half reaction. So before you add things together, you can always look to see if there's things that will cancel out. In this case, you'll notice that you can cancel out the 10 electrons from either side of that reaction, and then we can simply write down that collective redox reaction where we've got 10 chloride plus 2 nitrate plus 12 H+, and that will collectively yield 5 Cl2 plus N2 plus 6H2O. So we've added our two half reactions together, and we don't need to simplify this reaction anymore. However, there's a couple ways that you can check to make sure that your reaction is balanced. That's one of the beautiful things about redox reactions when you balance them, is you can always check if you're correct at the end. One thing you're going to do, just like we typically do when we balance a reaction, is that we're going to make sure that we have the same number of atoms on both sides. But this time around, we're also going to check to see that the charge is the same on both sides. That's just like what we did when we balanced electrons, and so that helps us know that we've got a successfully balanced redox reaction. So let's start with the number of atoms on either side. In the reactant, we have 10 chlorine atoms. We have 10 chlorine atoms on the product side. We have a total of 2 nitrogen atoms on the reactant side, 2 nitrogen atoms on the product side, 6 oxygen atoms on the reactant side, 6 oxygen atoms on the product side, 12 hydrogens, and 12 hydrogens on both sides of the reaction. So we can feel confident in saying we have the correct number of atoms on both sides. Now we can look at the charge. So we can simply add all of our charges together to see if the sides equal one another. They don't necessarily have to equal 0, we just need both sides to be equal to one another. So for the chloride, we have a -10 charge. For the nitrate, we have a -2 charge. For the hydrogen, we have a +12 charge. And all of those will collectively conveniently add up to 0. The other side is nice because it has charges for each of the molecules of 0. So we can feel confident in saying that we have the same charge on both sides. So if we wanted to balance a reaction in an acid, we have successfully balanced that redox reaction. You'll notice I gave you 10 steps. If you're balancing in an acid, you can stop after step 9. However, if you wanted to balance in a base, we might say that balance with hydroxide, balance under alkaline conditions, balance under basic conditions, all of those mean balancing in a base. So all you have to do is do steps 1 through 9, just like we've done, but then you also need to include a 10th step. That 10th step is simply neutralizing the H+ that's present so that we have hydroxide present instead, which would be basic conditions. So you'll notice in our redox reaction that we've written, we've got a +12 H+, so we can simply neutralize that by adding 12 hydroxides to both sides of the reaction. Whenever you add H+ to OH-, you should recall that that's going to form water. So instead of H+ and OH-, now we have 12 water molecules. And because we've done that, you'll notice that now we have water on both the reactant side and the product side. So we can simplify that for ourselves even further by canceling out the 6 waters on the product side and then having just 6 water molecules left on the reactant side. It's gotten a little messy at this point, so I'm going to rewrite this reaction one final time, this time as balanced in a base. So what we end up with are 10 Cl- plus 2 NO3 minus 1 plus 6 waters yields 5 Cl2 plus N2 plus 12 OH-. Just like we did in step 9, you can check to see if you have the same number of atoms and the same charge on each side. So we have 10 chlorine on both sides, 2 nitrogen on both sides, 12 oxygens on the reactant side, 12 oxygens on the product side, 12 hydrogens on both sides. So we have the same number of atoms on both sides. And then for charge, we have -10 plus -2 gives us a -12. And then on our product side, we also have a -12. So this time around, unlike our previous example, we don't have each side equal to 0. We have each side equal to a charge of -12, telling us that the reaction is balanced. So this gave you a walkthrough of the handout I've provided about balancing redox reactions. It really just takes a little bit of practice to remember the steps along the way, but if you follow the different checkpoints along the way, especially at step 7 where it says to double check that the electrons match the original assignments, and then checking in steps 9 or 10 depending upon what you're doing, you should be able to have confidence that you've successfully balanced redox reactions. Redox reactions are important for a wide variety of things in the form of energy transfer, environmental reactions, things that happen in your body. So it's really important to realize that as electrons get transferred, there's chemistry behind all of that.